Welcome everyone. I am Tauntud Aun. I'm Director of AIT Solutions, Asian Institute of Technology. I'll be the host for today's talk. Let me introduce of AIT Solutions and this talk. AIT Solutions is a unit in AIT, which is a consulting arm of the institute to provide the solutions to the industry by sharing and applying AIT's knowledge and expertise, as well as the research outcomes. Structural engineering solutions are our key expertise, and we provide the services in performance-based seismic design, wind tunnel testing, as well as the structural health monitoring services. Not only structural engineering services, we also provide the software development and IT services. We develop the customized software based on the needs of our clients. Our software development team work for not only in the structural engineering field, other engineering fields as well to meet the needs of our clients. In Meet the Expert Talk, we invite experts in the structural engineering and other allied fields to share their knowledge and experience over an online session. Today's talk will focus on the intricate relationship between wind, architectural forms, and structural configurations, and their role playing in the design of tall buildings. Let me introduce our speaker today. Engineer Stefano is a wind engineering specialist with an extensive experience directly involving in several hundred consultancy projects worldwide. He provides wind engineering services by means of experimental and numerical methods to designers and end clients. He also shares his knowledge and experience by participating in committees, working groups, and peer reviews of global professional wind engineering community. Currently, Engineer Stefano is a technical director and leading wind engineering team in WSP, UK's specialist group. Let me welcome Engineer Stefano to present tall buildings, wind forms, and structures. If you have any questions, please send the message in the chat box.
Right. Thank you so much to the entire team at AIT and AIT Solutions for the kind invite. Let me just share my screen. Hopefully you can all see this. Please shout if you don't. Right, so hello everybody. I'm not too sure where you guys are at the moment. So good morning, good afternoon, and good evening. Just to cover everybody, hope you are well and keeping safe during these difficult times. I've been asked to put together this talk to tell you about wind engineering in the context of tall buildings, and specifically I will talk about wind forms and structures. Right, so this is the outline of my presentation. For those who are perhaps not too familiar with what wind engineering is, I will give a bit of introduction, and then I will start covering and unpacking the three main components of the presentation. So wind, architecture, and structures. And then at the end, I will give you what are my personal thoughts really on where I think this industry is at the moment and where it's heading into the future. Right, so this is the official definition of wind engineering that has been adopted by the International Association of Wind Engineering. And as you can see, it's quite a powerful definition because it clearly shows how this field and science covers a very wide range of topics. So we are effectively going from studying the impact of new structures within the built environment and the effect that they have perhaps on pedestrian within the urban canopy, all the way to how wind interacts with buildings, the way it affects the design of the facade, the way it affects the design of the superstructure. So quite a powerful definition here. Despite the fact that wind tunnels have been around for best part of 120 years now, we had to wait roughly until the beginning of the 60s to actually see this very important paper appearing in the technical publications at the time. This was actually published through the proceedings of the Institution of Civil Engineers. And this is a very important paper. It sets the first building block, if you like, of modern wind engineering. It contains the very first framework of statistical treatment of wind loading on structures. So if you're not familiar with this paper, I highly recommend that you get a copy and read that. What is quite interesting to observe as well is that just a couple of years after the publication of this paper, there's this other paper that has been published by Smagorinsky. It was published very much in the context of weather forecasting, but it is quite powerful because effectively it contains the very first formulation of what is still used today as a model in the context of a large eddy simulation within CFD. So quite interesting to observe that, the birth of both, if you like, experimental and computational wind engineer is not that far apart. This is a powerful slide. I mean, it's taken from another paper by Alan Davenport. It shows what is called today the wind loading chain. And effectively, it shows how the relationship between wind, architecture, and structure are interlocked with each other. So we have typically, an initial input, which is the wind that contains obviously strength, directionality, exposure, and so forth. That obviously interacts with a first, if you like, filter function, which is the architectural form of the building, to actually raise to a series of wind pressures, wind loads acting on the structure. And then obviously these wind pressures are applied to the structure. There's a lateral stability system that resists these forces. And then the combination of the two give rises to effectively the wind-induced structural response. Okay, so what is interesting to observe is that there are effectively two potential loops here, and that's what are marked with the arrows at the top of the graph. So you can actually influence the response by obviously changing the structural system, but you can also do so by playing with the architecture, or ideally with both. In my opinion, playing with the architectural form is a very powerful way of controlling the response due to wind excitation. And I think moving ahead into the future with our quest to effectively reduce the carbon footprint of the structures that we're building, we will see a lot more work around the optimization of the forms of the buildings that we are designing. So in the context of wind, this is the first building block, the first link of the chain. And one of the most important one, really, because you can probably appreciate that a little bit of uncertainty on this parameter will have an important effect. It will propagate down the chain, producing, uncertainty that grows and grows by the time you go to the structural response. So this is what we think we know well. I say we think because obviously when it comes to events like extratropical depressions, think about gales, tropical storms, typhoons, for instance, these have been studied extensively in the course of the last decades. So we know how to treat them relatively well, I would say. Although I must say that, you know, when you start going above perhaps 400-500 meters, you know, there's still not a lot of information about how the models that we are currently using are actually behaving at full scale. So there is a little bit of uncertainty there, and we need to be mindful of that. Obviously, when you study a new wind climate, or you want to have more understanding about how different mechanisms work together, there's a lot of work that needs to happen in the sense of, you know, in the context of developing a detailed wind climate analysis for a specific site. Different type of mechanism, different type of storms needs to be separated. Their probability needs to be treated separately first and then combined back together. And obviously that has also an impact on the directionality. I've put on the right-hand side of this slide an extract, you might be familiar with it, from the report that was published by NIST in the context of the investigation on the progressive collapse of the World Trade Center towers in New York. It's all publicly available, you can download a copy. But obviously I was quite interested in the wind part. As part of the study, parallel wind tunnel testing was commissioned subsequent to the collapse, just to gain a more refined, a better understanding of the wind loading on the two structures. And what was interesting to find is that the two labs that were involved ended up with quite large discrepancies when it came to definition of wind loading over 20 moments, for instance. They were something of the order of 25% apart from each other. And in my experience, and I've been involved quite a lot in peer review and parallel wind tunnel testing, this is very much caused by a mismatch on the wind climate model. So typically, if you can align the wind climate model right from the beginning, then you move through the chain, and then at the end you end up with relatively small discrepancies. Believe it or not, still today, despite you know, this science has been around for best part of 60 years, there isn't a unified and internationally agreed, if you like, way of treating the directionality of these extreme events in the context of wind loading, and that can be sometimes quite challenging. Obviously, if you gather data, if you study data from weather centers, if you study data from airports, always be careful, try to understand where the anemometer was positioned, what type of anemometer it was it a rooftop? Those comes with a lot of problems. There were proximity effect. Having a good understanding of this is essential. And if you don't know enough, well, get as much data from different stations as possible and compare them with each other, because if you intend to rely on this for design purposes, you need to be pretty sure about what you're doing. Obviously, studying the effect of the topology and characteristics of terrains around the site is important. These days, things are a little bit easier, I must say, because there's a lot of digital information out there that is publicly available on land usage. So you can use those to characterize the aerodynamic roughness. And then obviously developing you know, variation of mean wind speed, intensity of turbulence, length scale, gas speed, you name it, just to get a good understanding of what sort of forces you might end up expecting. As you can see from this slide, you know, if you move between places without, say, hurricanes or typhoon to places with typhoon, you can get, you know, a huge increase in pressures, you know, sometimes up to a factor of 4. Right, so this slide is about what we don't know so well yet. There's a huge amount of research going on in this field. These are very much transient events. They can often come and go in the space of a matter of, you know, minutes, you know, maximum, say, 20 minutes, half an hour, perhaps. Thunderstorm, tornadoes are a good example. There's still a lot of research going on, so you need to be aware of this. You need to reach out to an expert if you're not too sure about how to treat these events. It's probably fair to say that the two biggest research centers in the world at the moment in these fields are the ones at the University of Genova in Italy and Western University in Canada. And as you can see, these events can happen, very suddenly. If you couple this with perhaps structures which are temporary structures, well, things can become quite tricky, especially if during the design process you started actually reducing wind speeds to actually save on material, etc., etc. The directionality of this event is, very difficult to establish. These downbursts can happen at different locations, and therefore the flow, the direction where the flow is coming from is very much uncertain. This is just because the size of these events is incredibly smaller compared to the size of a large extratropical depression, for instance. So forms. So forms is all about architecture. That's our first filter function, if you like. And as you can see, this is quite a nice slide that shows you, the power, if you like, of three-dimensionality. So you move from 2D to 3D forms in the context of aerodynamic force coefficient, in this case, drag specifically. As you can see, by promoting three-dimensionality, you can actually gain a lot of reduction in loading. You might ask yourself, why am I talking about three-dimensionality when we are looking at tall buildings, which are, typically tall and slender structures? Well, there are opportunities to actually promote the dimensionality of the flow, especially by playing and tweaking the top part of the structure, and that is incredibly beneficial in so many ways, and I'll come back to this. But obviously, we can't be too much obsessed with drag, I must say. There are the important factors that we need to look at, of course. This slide is very much about describing how the turbulent flow interacts with the prismatic structures. As you can see, the flow, especially of the top third of the building, is generally highly three-dimensional, although, as I said before, this can be enhanced even more. And then typically what happens from, say, roughly 2/3 of the height down to street level, while you have a downward movement of hair. And that's what does typically make the base around these tall buildings particularly windy. So these are quite challenging things to consider. Obviously, we are interested in comfort, but also safety of pedestrian walking through the cities. There's a tremendous amount of work that is typically done in making sure that situations like the one shown in this video are very much avoided. Another good slide just to show how drag can vary between different forms. As you can see, one of the perhaps worst performing form in terms of drag is a triangular form. Triangular forms comes with quite a lot of other problems, and I'll mention that later on. And this is quite an interesting slide because it shows that also corner treatment are quite helpful in reducing the overall drag acting on the structure. And what is interesting to see is that, perhaps one of the best performing extrusion is a circular cylinder. Obviously, circular cylinder comes with other problems attached to it. And this is why I put together this slide, just to reinforce the fact that we're not designing cars, we're designing tall buildings. So it's not all about drag. Obviously, even when you push into the supercars regime aerodynamically, you're not just worried about drag, you're worried about downforce, of course. But this is just to put, the emphasis on the fact that, yes, drag is important, but it's just, half the picture, if you like. So this is the phenomenon that typically we are interested in tall buildings, which we try to address and tackle. It's called vortex shedding. In this video, you have wind moving from left to right. You have an extrusion of a form spanning across the wind tunnel in this case. As you can see, unsteady vortices are peeled off from this form. These are happening in an alternate fashion. And because of this, the net effect on the structure is a force that in this video is obviously acting up and down, but in the context of tall building generates lateral forces. Right, so sometimes I show this video and people say, okay, well, this is just happening in the wind tunnel, it's not happening in reality. This is an example. Obviously, it's not a tall building, but it's a very slender structure. It's a circular hollow section, probably very low damping, as I said, very slender. And there's a storm going on, perhaps not a big storm, but because of the small cross section of the object, you don't need a lot of speed to get this going, really. And yeah, every time I show this video, I never understand why people keeps on driving really under this. Not least because, as you will see in a little while, one of the panels will suddenly slide off. But this is just very much what can happen. So that's what we need to look out for. And this is a photo of the top of the John Hancock Center in Chicago, where you can see low-level clouds interacting with the top of the building. So you can see this vortex being shed at full scale. Obviously, when these vortices are shed at a frequency that is relatively close to the frequency of the building, you can have large excitation. It's a little bit like plucking the chord, the string of guitar, really. And this is what sometimes can happen. So you look into the wind-induced response. Believe it or not, this video is taken from a tall building that is not incredibly tall at all, and you can probably guess that actually because you can see that the excitation is not going in the direction in the longer direction of the swimming pool, but it's going across that. And yeah, this is the case. Obviously, there's a fair amount of excitation. There's typhoon going on in this case, of course, but these are the things that can actually happen. Obviously, that video was very much looking at serviceability, if you like, but still, those are quite important, and should be studied and considered. All shapes produce vortex shedding. You can't really escape that. There's a parameter that is called the Strual number. It's a non-dimensional quantity, which effectively tells you about how these vortices are shed from a given form. So it kind of brings together wind speed, dimension of the cross section of the object, and the frequency at which these vortices are shed. And this is, again, looking at, in this case, spectra. So very much looking at the energy associated with this lateral excitation induced by vortex shedding for different forms. And they are plotted versus effectively reduced frequency, okay? But you can think about it in terms of, frequency or wind speed, if you like, just a question of changing the way the data are presented, really. But as you can see, especially if you look at the first two slides, sometimes small treatment to corners can be incredibly beneficial in reducing the response. Any reduction that you see in this graph in the y-axis translate immediately into a reduction of dynamic excitation on the building, reduction in wind-induced acceleration, etc., etc. Okay, so these are quite important. This is an example of a building, 330 meters tall, approximately, in Beijing. I had the pleasure to work on this a long time ago. And believe it or not, this small corner adjustment, the actual corner modification becomes slightly bigger by the time you go closer to the top. But this, compared to an extruded square form with sharp edges was able to reduce the overturning moment of about 25%. So not small numbers. Taper forms, of course, very attractive, very important. You know, they give you the opportunity to put the stiffness where it's needed, obviously the base, reduce the mass where you don't want it. So that's all great stuff, no problem with that. Because of the taper, you also reduce the frontal area at the top of the building, another tick. And obviously by changing the cross-section dimension while you move up the tower, well, you reduce the possibility of creating effectively a well-correlated vortex shedding acting over a large portion of the structure. So those are all positive aspects. One of the slight complication of taper structure, and I'll come back to this later on in the presentation, is that typically a taper form compared to an extrusion, it does tend to have slightly higher frequency for the first mode, which is great. But at the same time, what it does tend to bring down the frequency of the second and third order modes. So that's that sometimes dynamically can actually be a challenge. But I'll come back to that. So if you want to optimize a form, these are some advice that I can give you. I mean, you can be as advanced as you like with this, really. You can start by plotting a series of curves. So, you know, you studied your wind climate model, you have a good understanding of design speed for your site for different return period. You can plot those curves, you know, no problem. And those are the color ones that you can see here. At the same time, you have a rough idea of how the shape of the building looks like, what sort of geometry it has. Is it a taper form, for instance? What's the cross-section dimension at the base, and so forth. And you can, for each height, derive very approximately the critical wind speed for water shedding. And then you can study where these curves are interacting with each other. So you can actually say, okay, for this building, for this particular condition, for this form, I'm expecting to have some challenges associated with water shedding, very much in the context of serviceability, perhaps 10-year return period acceleration, or perhaps you end up with something that is telling you, well, actually acceleration might not be too badly affected. ULS loading are perhaps more affected. But the powerful of this is that you can actually test it and change things. So you can maybe adjust a little bit the footprint of the building. You can perhaps play with the corners. You can perhaps play also with the stiffness of the building. Obviously, this is an exercise that it needs to happen, you know, almost on day zero, right? When almost there's, I wouldn't say there isn't an architect yet, but kind of, right? And obviously, you can end up with the best case scenario where you got rid of the water shedding, although you can appreciate that this is very much a non-convex problem, right? So there are different minima here. You can, you know, juggle and optimize things differently. But this is always a good starting point. And as I said, it can get as complex as you like. It can be coupled with, you know, CFD, and we'll see that in a little while. And it can be quite powerful. This is a tall building, perhaps one of my favorite ones that I had the pleasure to be working on. It's a 530-meter tall building in Tianjin in China. I think somebody has the audio on. It would be good if it could be turned to mute, please. Thank you. This is a highly aerodynamically optimized form. This building, it has no dampers. It's been developed together with the architects and engineer of the scheme, which were back then SOM. And we took this through an extensive series of wind tunnel testing. You know, a lot of variation of these forms have been tested. And, you know, the curvature, the way the cross-section changes with height, the nature of the crown, which as you can see is relatively open, relatively transparent to the wind, that again promotes the three-dimensionality of the flow. They've all been studied and fine-tuned specifically for this site. So optimum forms needs to be site-specific. That's quite important. Sometimes people say, well, what's a perfect form? Well, you know, as I said, it needs to be fine-tuned to the characteristics, the wind characteristics of the site. But in general, if you want something that ticks so many boxes, well, let's do this. Let's start with this form, which obviously has a relatively low drag. When it gets studied, both numerically and experimentally, comes with a lot of challenges. Let's forget about those for a moment. Obviously, it comes with quite a lot of problems associated with water shedding. Luckily, when it comes to tall buildings, we have the opportunity to actually do something with this form. We're not dealing with chimneys. We are not dealing with deep water risers, right? We can cut this across. We can promote flow going through this form so that the wake that is developed downstream because of the water shedding gets re-energized. So what we are doing is we are injecting air into the wake. The wake becomes more chaotic, and therefore the regular pattern of the vortices that you've seen before kind of goes away, or it gets significantly reduced. Now, this is a bit difficult, obviously, to, it would work just on some direction. So we need to actually tweak that a little bit and perhaps end up with something like this. Ironically, this is a form that was used for the Nahil Tower in Dubai, which unfortunately never happened. It was a victim of the 2008 financial crash. But this was designed by Woods Bagot with WSP as structural engineers, and as you can see, this form was ticking a huge amount of boxes. Obviously, you need a lot of footprint to do this, but don't forget that this building was approximately 1 kilometer tall. So these are good indication of what perhaps you should consider when you go into those sort of heights. Perhaps a normal building doesn't quite work anymore. You probably need buildings linked within each other, perhaps within a mega frame solution. Okay. So wind pressures, this is what we are trying to measure in the wind tunnel, trying to resolve numerically in CFD. Obviously, one of the challenges with wind is that it is invisible. So any way we have to actually visualize what's happening, it's a great thing. And this is an artistic installation that was put up in the Randall Museum in San Francisco. They had more than 600 vanes, these tiny little plates which could spin, and you got the opportunity to visualize wind. So this is what actually happens. Sometimes you have small gusts that just kind of randomly almost spinning some of these vanes across this facade, and then all of a sudden you have all these vanes realigning to get a gust of the size have a lot of pressure sensors on these buildings, and this is basically what's happening typically. Okay, so I know that sometimes people are interested in taking this data from the wind tunnel and plugging them in directly into an FE model. That's a great thing to do, no problem with that at all. But don't forget that by running time history directly from the wind tunnel, obviously it needs to be scaled up to full scale, etc. But by running that sort of simulation, the peak that you get by way of response, while as the maximum of that time history, perhaps, well, that's not really the statistical peak. Okay, so there's a fair bit more work that needs to be done, and that can be quite time consuming. Time history is a great thing, but trust me, a little bit more painful than frequency domain. Wind tunnel testing has been used extensively, as I said, for decades now. There are a lot of technology that you can use, different techniques, force balance, high frequency pressure integration, aeroelastic, you name it. So, you know, these are quite important and extensively used still today. These slides actually tries to go a little bit deeper into the wind pressure field. So this is a piece of work that I did some time ago. This building was, you know, relatively prismatic form, about 200, 240 meter tall, something like that. And we were able, through this technique, which is called POD, proper orthogonal decomposition, we're able to peel off the different modes of the pressure field. So as you have modes of vibration in structure, and sometimes you can say, well, actually, to define the response, I just need maybe 3 modes of vibration, perhaps, or 5 modes of vibration. I don't need all the modes. I don't need many modes. Similar things happen with the pressure field. So you can see here, you know, in the top left-hand corner, clearly in a long wind mode. You move to the right, and you have a vortex shedding mode with a plus and minus on the side faces. Then the third mode is, well, an antisymmetric mode in the long wind direction, kind of interesting. And then you have a fourth mode, which is antisymmetric on the vortex shedding. You know, for a building of this form, in a relatively isolated condition, I must say, that's probably all you need. Or you can even get away probably with the first 2. So if you're actually interested in time history analysis and you want to reduce the complexity of time history that you're actually working with, POD might be a good tool to use to actually make your life a little bit easier. If you actually are in a built-up environment, things are not that straightforward. You need far more modes to consider, so keep that in mind. And obviously, great difference between a long wind and a crosswind, especially when it comes to, you know, looking at it from the point of view of frequency domain. You know, a long wind has this distribution of energy associated with excitation that typically decays in a monotonic fashion, if you like, while vortex shedding from many forms, it does tend to come with this, you know, peak of the response. And obviously, you know, the closer you get to that peak, without taking into account duly fluid structure interaction, the trickier it gets. So structures, I'll be looking at structures very much closely with the structure response at this stage. There are a lot of structural systems that I use these days. I mean, it's the list is really incredibly long. I must say that core plus outrigger is probably one of the most common one, to be quite frank with you. So what you're trying to do here is very much have well, typically belt trusses, bringing together the columns on the perimeter of the building and connecting them with outriggers to the core, so the columns are working together with the core. So you're trying to actually improve and minimize the deflection of the building by doing so. This is a system that's been around, you know, for a very long time. It was tried for the very first time by Pierluigi Nervi, an Italian engineer, for a building in Montreal in the 60s. So 60s have been, you know, quite special in so many ways, as you can see. When you go into super tall, super slender, well, there are these days a lot of other structural systems that are used and contemplated. You know, buttress core is a good example. It's not a coincidence that, you know, what are going to be the 2 tallest buildings in the world have this structural system. And then, you know, also frame tubes, you know, quite important when you go into super slender regime. So parameters that actually affect and govern the wind-induced dynamic excitation and structure response of tall buildings are obviously inertia, structural frequencies, damping. Okay, inertia, well, it's very difficult to play with that. I mean, reinforced concrete tall building has a bulk density of about, you know, give or take 300 kilogram per meter cube. So it weighs roughly 1/3 of the water. That's it. Steel building might be 1/4, water, something of that order. Yes, you can increase the thickness of some floors, perhaps towards the top, to increase the model mass, etc., etc. Those solutions are definitely possible. In the context of reducing the carbon footprint of this building, well, it might not be, a very smart move. Playing with the form, we've seen that before, very advantageous. Introducing additional damping might be an interesting way forward in some projects. This is an important slide. It just, if you work in a country where the code doesn't look directly at ULS speeds, as it happens in Europe these days, well, you need to be mindful of this. If you have strong vortex shedding and your load combination factors have been effectively calibrated and developed, assuming that the response grows with wind speed square, while if you have strong vortex shedding and you just look at, say, 50-year return period, 100-year return period, and then multiply those to go to ULS, while you might end up being with unconservative numbers. So that's something to be very much aware of. Doesn't happen if your code pushes you to go directly to ULS, as it happens, with the Australian code, with the American code, and so forth. High modes of vibration in the context of super tall. I put a couple of slides on this because I mentioned that before and I wanted to come back to this. I put side by side these two buildings. One is 600 meter tall, the other one is 700 meter tall. I've been involved myself with both. The 600 meter one has a very, very gentle taper. The 700 one has a strong taper. The very top of this 700 meter one actually has a large spire, which is roughly 120 meter tall. So it could be a tall building in its own right, sitting on top of another big tall building, right? What is interesting to observe is that, when we started this 600 meter tall building, we took into account up to mode number 8. But from a point of view of wind-induced peak acceleration, for instance, we could have just analyzed the first 3 modes, the first fundamental modes of vibration, and we could have ended up with a response which was roughly 97% of the total response. So higher modes play very, very little in this case. And interesting to observe the difference in the ratio between modal mass and total mass, roughly 20% here and a very small number here. And that's because of this spire actually doing something special. So in this case, actually, at the base of the spire, which is not the tip of the building, ignoring higher order modes of vibration, while can actually mean that you end up being something like 15% on the non-conservative side. If you look at the very tip of the structure, well, you could be 40% out. So quite important consideration. Super slender. While are higher modes vibration important in super slender buildings? Well, it very much depends on where you are. It depends very much on the wind climate. So I put 3 different wind climates here: London, New York, and Shenzhen. And I drew some horizontal lines just showing you the critical wind speed associated with water shedding. So typically, you do tend to have this resonant behavior at very, very common wind speeds, far more frequent than 1 year return period. That's for the first order mode. If you have a form that effectively is a little bit more, if you like, organic, so yes, perhaps rounded corners, and if you are actually in a climate where you do tend to have hurricanes or typhoon, while the possibility of having the second order modes of vibration to interact perhaps with the ULS speeds is actually quite high and very much possible. Sometimes extra damping is needed on structures. There are different types of devices. Some of those are passive, some of those are active. I must say that active application in the context of vertical structure, there are not so many outside Japan, probably it's fair to say. There's only one example that has been delivered here in the UK that I'm aware of course. And Again, in the context of passive, there are different devices that can be used. Some of those can be used to actually take advantage, from serviceability all the way to strength design, and some of those are just, used typically to control serviceability, control wind-induced acceleration, for instance. An example of a passive device is a tuned liquid column dampers. This is an example. So when you design this, there's quite a lot of work that needs to happen, both from CFD side of things and experimentally. So these devices are, they're not small, they're quite big. They take out a lot of space, no doubt about it, but they're quite simple. In this particular configuration, they are, their non-linearity is not that great, which is good. And in this case, as you can see, this movement up and down in the vertical columns induces movement, left to right within the horizontal duct, and it's the flow going through this grid system that is typically constructed using, steel profiles. That's what creates a dissipation of energy. Okay, very low maintenance, not incredibly expensive, but as I said, they can take out a lot of space. Two mass damper in the pendulum solution, as you can see from the right hand side of this slide. Again, great devices if you actually have very long period while these start becoming very, very long, so they take out a lot of space. In order to avoid that, you need to actually fold them up once, fold them up twice, end up with relatively more complex mechanical arrangement. So you have a frame within a frame within a frame, like you have here in this picture. In this configuration, they can become quite compact and quite effective. But obviously, you would take this only up to control of serviceability, not strength design. Viscoelastic damper, which is what the video on the left-hand side of the slide actually shows. Well, if you have enough redundancy in the system, if you introduce this throughout the structure, and you could end up having, perhaps even hundreds of those, deployed across a sizable tall building, then the advantage of this can be taken to the strength design, and therefore you can actually take advantage of those. Be a little bit careful, because traditionally these have been developed very much to deal with seismic forces, and the duration of those events is relatively small, I must say, compared to a windstorm. So if you've got a windstorm that could go on for hours, and sometimes the performance of this rubber material that is between the steel plates deteriorates slightly with increased temperature due to the friction that is going between these plates. So, there are materials that behave better than others. And obviously full scale measurements, very important. We are not doing, as a community, enough of them, I must say. There are a lot of challenges around them, because nobody is particularly interested to pay or know much about how this building behaves. But ultimately, I do think that if we want to build better buildings and perhaps reduce the conservatism that I believe personally is still present in what we are doing, we should do a lot more of this. This is an example of a full-scale campaign I've been involved with myself. This was a 240-meter tall building. We're measuring different quantities. This was done very much in the context of tuning a damper that was installed at the top of the building. Those are rare opportunities that you have to actually get involved with this type of work. As you can see, damping does vary a little bit with the peak acceleration. It's not a fixed number. It's actually not increasing all the time. There's a point beyond which it does tend to kind of levels off before other mechanism comes to play, of course. But these are important, because they're very valuable exercise. They give you the opportunity to take the data that you measure, plug back into your analytical model that looks at the post-processing of the wind tunnel data, and you can compare and see how you've been doing when you did the prediction with the wind tunnel. And as you can see in this case, prediction between wind tunnel testing and post case, they were, for this specific storm that we were looking at, particularly good. So what is next? And this is my last few slides, really. So for a very long time, we've been treating computational wind engineering and experimental wind engineering very separately. It's fair to say that from that paper that I showed you, 1963, it took best part of 30 years before CFD began to be used in the context of this complex problem of buildings in the built environment. And this is simply because the flow is very complex. It's, bluff body aerodynamics, unsteady flow, turbulent flow. It doesn't get any more complicated than that. So there are reasons for this, but things are changing these days. We are, very much breaking down these barriers. We're bringing these two tools together. I think this is probably fair to say where we are in most part of the industry. The two tools are very much working together. Sometimes it's difficult because you need to be very much on top of both. Not many people can have access to both design tools. But ultimately, where I would like to this industry to go is to actually have, close this loop really. Think about what happens typically in Formula One. You have a lot of CFD, a lot of wind tunnel testing, and then you have track data. You test how the car performs. Well, we don't seem to be doing enough of that. We do a lot of design, but then we don't test it. At the end of the day, CFD doesn't need to match the wind tunnel. That's not the purpose of it. The purpose of this is we have two tools. They're very powerful. They have their own pros and cons, no doubt about it. But ultimately, they need to help us designing real structures. So that's very important. So can we push CFD into their solution of structural wind loading? Well, we're making a lot of good progress, I must say. There are different ways of doing this. Obviously, you need to forget about standard, CFD, run simulation. They don't work for this type of application, not at all. You need to push a bit harder. You need to go into, if not full LES, at least hybrid runs LES, like DES, for instance. And those can actually be quite powerful. There are different ways of actually simulating the boundary condition. Some people like to create a replica, effectively, of the wind tunnel. It's quite expensive to do that because you got a lot of cells that are wasted in generating the oncoming flow. Some people quite like to use precursor database method. So you do similarly, you have this wind tunnel, this, as people call virtual wind tunnel. I hate this word, by the way. And they actually sample the data. They sample the data, they store them in a huge database, and they use them in the next simulation. So it's kind of nested, if you like. Interesting application. I don't think they're particularly elegant, in my opinion. You can just simulate and store a lot of data, just because you can. It's not an excuse, really. Synthetic turbulence generators are, in my opinion, the way forward, for sure. And they are quite powerful, especially when they're coupled with form finding and optimization algorithm, which are bringing together, a bag of different type of data. Some of those are perhaps low fidelity data, but they're supplemented with, high resolution, high quality CFD data, and perhaps also coupled with wind tunnel data. If you want to see how CFD can compare these days with a DES simulation using synthetic turbulence, and compare it against a wind tunnel experiment on a sizable tall building, this is where we are these days. So we are doing, I think, quite well, especially during the early days when you're looking at optimization. Well, these tools can definitely be used, no doubt about it. They become a lot more challenging, no doubt, when you have an incredibly built-up terrain. But we are making definitely progress. And this is just a visualization of the tall building. I just presented the spectra for, just to show you, what it can be achieved. These are by all means, quite complex simulations, and they can be, also a little bit expensive. But some people say, well, these are incredibly more expensive than a wind tunnel test. Well, they are not. trust me. So where is the future? I mean, will CFD ever replace wind tunnels? I think that, in all frankness, is their own question. I think, as I said before, CFD and wind tunnel tests are two design tools as far as I'm concerned. And every time we have the opportunity to bring them together for the benefit of the design, to actually build, to design and build better structures, structure that comes with a much lower carbon footprint, well, those are opportunities that needs to be taken. I'm mindful that it might not happen all the time, but you know, there is an education process that needs to happen, especially together with the client, because this is, I believe, the way forward. Thank you very much, everybody. And if you have any questions, just feel free to type them in. Thank you.
Thank you, Stefano, for sharing your extensive experience. This kind of knowledge we can acquire from the person who has a lot of experience in wind engineering. I hope we all can learn the importance of the forms influencing on the wind response of the building, and also the methods and tools to control the wind response in structural design of tall buildings. In AIT, we also offer a civil and infrastructure department in AIT is offering the professional master in structural design of tall building for the practicing engineers. It is a blended program, online and in-class session. The engineers do not need to leave their job. So it is the professional master program. The duration is 2 years to 5 years. So if you are interested in that professional master program, you can visit our website, solutions.ait.ac.th/pmtb. So let's continue the Q&A session.
Sure. How do you want to do this? Shall I go through the question and answer them myself? Is it okay with you guys?
It is okay.
Yeah. Okay, so we got a question from Shiba Mishra. So the question says, what measures are taken to avoid air and mist and smoke found near tall buildings in airport zones? When the Andaman Sea wind strikes tall building in Bangkok, there is chance of corrosion. What measures are taken against it? Okay, that's perfect. That's very handy. Thank you. Well, I mean, it's a good question. I mean, all that work that that video that I showed you before, where people have been blown down. I think it was a video taken in the Netherlands. So during those strong winds, there's obviously, as I said, there's a lot of work that actually takes place these days in making sure that those events do not happen. There are other parts of the world where you do tend to have very, very strong storms, but they do not happen very frequently. So most of the time you have relatively calm winds, and believe it or not, this is one of the case for Hong Kong. You know, when you have no typhoons, it's actually relatively calm. And one of the challenge with those calm weather is that within the urban fabric, you can actually, especially in built up and densely built up zones, you can end up with very low air quality. So you got pockets of polluted air being trapped between buildings. So the trend in that sense is to actually play with the massing of some of these buildings. This needs to be done, I'm afraid, very much at master plan stage, really. You know, introduce, for instance, gaps and voids, but also play with the orientation of this building to try to actually, instead of doing what we are doing in Europe or North America, prevent, you know, excessive winds at street level. In this part of the world, you want to actually promote that. You want to maximize that. So you can actually have fresh air flashing out these pockets of pollution. So I'm not sure if that answered the question, but that's at least my best stab at it. If that person wants to take this further, you know, he or she can just drop me a message, and I'll be happy to discuss this more. Next question is most country 3-second gas speeds are used only 10-minute surface. Seriously satisfied for designer has building restriction. Yeah, I mean, it's a good question. I mean, typically these days, you know, modern anemometers are actually sampling at incredibly much higher frequency than this. You know, you go at least into, you know, 10 hertz, you know, you would hope. But ultimately, you have wind models that are allowing you to convert, you know, any sort of duration of gustiness. So you can go from 3 seconds to 10-minute mean to mean hourly to 1 second, you name it. So those conversions are, you know, relatively straightforward to handle, to be honest. Ultimately, when you look at an experiment, especially in the wind tunnel, most of the time you do work and set up the experiment using, you know, average speed, mean hourly speed, or 10 minutes mean speed, you know. But, you know, the effect of the dynamics and everything gets calculated, you know, during the post-processing phase, either in the frequency domain or in the time domain, you know, so that takes care of itself, really. Will the presentation be available online? I believe the presentation is being recorded. It's probably a question, you know,
Yes,
to
we
be
will
answered
share
by
the
the
video.
IT team, yeah.
Yes. Yes, we recorded and we will share that video.
Good. I'm not sure if there are other questions.
Yes, there is one question. What softwares can do CFD analysis and wind tunnel test? How it differs?
Right. So, I mean, as you can probably appreciate, there are not many wind tunnels around the world that do this type of work, at least commercially. And every lab does tend to have its own software to post-process and analyze the wind tunnel data. We have, for instance, a WSP, a software that is quite versatile in the sense that it's able to interact with different types of outputs from different labs that we typically work with, you know, on a weekly basis. But those are very much bespoke. When it comes to CFD, there are obviously a bunch of commercial softwares that are available. In-house, we don't use them very much. We do use most of the time open source softwares like OpenFOAM. We think it's, you know, incredibly powerful. It gives you the opportunity to, if you want, even, you know, get your hand dirty and change the code yourself, which is quite powerful and helpful when you're trying to resolve and achieve something relatively niche that is not coming as part of the package, if you like.
Stefano, okay, one last question. Are there any structural techniques to reduce effect of wind load for very large billboards with several piers?
All right, so you're talking about billboards. I mean, billboards are very tricky, I must say. I'm not sure where this question is coming from. Billboards are very tricky because there are different things that you need to consider. You need to, first of all, make sure that they are aerodynamically stable. So that's nothing to do really with conventional strength design. You need to make sure that they do not suffer from aerodynamic instabilities, which could actually lead to structural collapse. So these are calculations that can be done with some codes, with not all codes of practice, but they can definitely be done. You need to go back to basics a bit. So you need to look for instabilities of flat plate to start with when you begin your research. And then obviously there is the strength part, especially in the context of torsional excitation. And when you do that, depending on which part of the world you are, you need to be a little bit careful because these are structures that are quite close to the ground. And if you work in a part of the world where there are severe thunderstorms, well, things can get quite tricky. If memory serves, the Thai wind code actually has a very, very good formulation to actually play with fine-tune, if you like, the gas factor to deal with this type of transient event, specifically in the context of billboard. And that's I believe, a piece of work that was done by Professor Penum from AIT, which I think is probably one of the only piece of advice in the context of billboard in thunderstorm-driven wind climate that I'm at least aware of. So you might want to take a look at that as well.
Okay, thank you very much, Stefano, for your time. And thank you everyone for joining this session. So I hope to see you in coming talks. Please stay safe. Have a good evening. Thank you.
Thank you very much, everybody. Speak soon. Thank you.